Okay, so we're going to just talk about water. The last section in your book is all, in that chapter 10 is all about water and its special properties because it's a little different than most liquids and solids. So, and it's all because of its structure. And so if we drew the Lewis dot structure, remember these? You have, it's a tetrahedral shape, and so we do have an angle of 105, and it's a bent shape. Tetrahedral, I guess, when you take into account the lone electrons, but then if you don't take those into account, it's bent. But because it's polar, remember we have polar bonds or nonpolar bonds. It's more negative towards the oxygen, more positive towards the hydrogen. So the negatives from another water molecule will be attracted to the positive ends of this water molecule, and it forms what's called the hydrogen bond. We usually use a dotted line to show that. And then you might also have another, let's say another hydrogen right here. So this one is hydrogen bonded to that oxygen. And then it just keeps making this big structure. They hydrogen bond within each other. This polarity and hydrogen bonding that occurs makes the boiling point of water very high compared to its mass, compared to molecules of similar mass, which is why water is a liquid at room temperature. If it weren't for the polarity, it would be a gas at room temperature. And we would not have life on Earth, probably. Okay. So it's all because of that hydrogen bonding that occurs. This is just showing some water molecules arranging themselves. In liquids, the hydrogen bonds are continually breaking and reforming as the molecules move past each other, since liquids are fluid. When it becomes ice, a solid, they arrange themselves in a more rigid structure, and there becomes a lot of air packets or little spaces in between the molecules, and that's why ice expands. And it's also why ice floats, because it's less dense than water. When it's less dense, that's an important thing for aquatic life, especially. If in a pond or a lake, if the ice were more dense than water, it would sink to the bottom, and that would push all the liquid water closer to the surface, and eventually would completely solidify. It would all turn to ice, and would anything be able to survive? No, right? So it's important for aquatic life. And then you guys have, does anyone actually have ice cube trays instead of just a ice maker in your fridge? So when you put water in there, you've seen it expand. Have you seen when, even though it stays in the freezer, there gets to be less and less ice though? You noticed that before? If it's been in there a couple weeks. And that is actually an example of sublimation. So even though it's in the freezer, there's a defrost setting that those kind of, like your freezer combo has, and it some of that water will turn directly into the gas stage, and then it freezes on the outside. Like if you ever have frost on the outside of your freezer. Yeah. Mm-hmm. Yep, that would be. Well, no, that is the water vapor in the air condensing in the air. Mm-hmm. Oh. Mm-hmm. Yep. Okay, so this is just a picture of how liquid water, they're a little closer together because they're moving and the hydrogen bonds are breaking and reforming, whereas ice, there's those packets of emptiness in between because they arrange themselves with the positive and negative ends pointing towards each other.
So is that like what it looks like? That's what creates like snowflakes, frost, like the bonds.
Okay, we should know some of these physical properties like the freezing and boiling point. Molar heat of fusion, so remember the last lecture we talked about the molar heat of fusion is the energy it takes to, it would be melt or freeze, so liquid to solid or solid to liquid, the amount of energy it takes to melt or freeze 1 mole of that substance, in this case it's water. So it takes 6.009 kilojoules of energy to melt or freeze 1 mole of water. And then molar heat of vaporization is from the gas to liquid or liquid to gas stage. And so if it has, it will either gain or lose 40.79 kilojoules of energy per mole of water that you're boiling or condensing. And those are constants. Each substance has its own constant, so ethanol would have a different molar heat of fusion and molar heat of vaporization than water. But it would always stay the same for that substance. You will be given these numbers, so you don't have to memorize them. Okay? But we're going to use them here. So how much heat energy, how many kilojoules of energy is absorbed when 47.9 grams of ice melts? So I'm going to have to use, in order to get to energy, I'm going to have to use the heat of fusion or vaporization. Which one? Ice melting. Fusion. So it's the liquid to solid and solid to liquid. And that is so we're going to use this like a conversion factor, just like we did in that last lecture. But you have 47.0 grams of water. Can I use this number yet? No. What do I have to do first? 2 moles. So the molar mass is 18.02. Whoops. Okay. And now I can use this number because we have moles here, so that means 1 mole of H2O needs to go on the bottom, and that would be 6.009 kilojoules of energy. So it takes 15.67 kilojoules of energy to melt 47 grams of ice. Questions on that? Okay. Now 15.67. Whoops. Oh, I'd say there's going to be multiple choice questions also. Mm-hmm.
More of these?
Like everything up in this red.
Yeah. So how much heat energy is absorbed when the same mass of liquid water boils? So this time, instead of using delta heat of fusion, we're going to use vaporization, which was 40.79 kilojoules. But it's the same process, right? So we need to change 47 grams of water, liquid water. So we have 18.02 grams of water for 1 mole of water. And then we can use our molar heat of vaporization, because 1 mole of water requires 40.79 kilojoules of energy. Point what? 39 kilojoules. So you can see it takes a lot more energy to melt or to boil off 47 grams of water than to melt 47 grams of ice. Okay, we have 2 more problems. The 6.009, yeah. But you'll have to figure out which one do I use. Do I use vaporization or do I use fusion? I'll give you both numbers. So remember, fusion is any liquid to solid or solid to liquid. Vaporization is liquid to gas or gas to liquid. Depends on the phase change that you're dealing with. Think of, well, vaporization has to do something with gas, right? Because it's always about gas state. And then fusion, I think of sticking together, so it has the solids are the most stuck together. The molecules aren't moving; they're fused more, and so it'd be anything to do with solid, solid to liquid, liquid to solid. Okay, so this time we have 506 grams of water. You guys tell me what I need to do. It is. So we would want to use delta HF. So these. Should have quite a bit more. What'd you get, Colton? There we go. Okay, this last one, last problem, and then we'll be done. It gives us the energy that was required, or that was released. And we had to figure out how much water did we have, or how much water. So this time, and we're condensing, so we're using fusion or vaporization? Vaporization. So this time we want to start with the energy that we have, which is 4.97 times 10 to the 5th. With kilojoules of energy, and we got to figure out mass. So we can use the same conversion factor, we just flip it because we need our units to cancel out. And then we convert moles of water into grams of water. Pretty much backwards. We just flipped everything. And then just make sure 18 has to be on top because we need the units to cancel out. You should, because this is 10 to the 5th. This number is very large. See? Or you have 2.196 times 10 to the 5th. If you wanted in scientific notation. Any questions? Okay, then here's your chapter review. It's due Friday. Whoops. And this is for the old book, but for the new book online and stuff. No. Is there? Does someone have a chemistry book out? One of the new ones? Back here. I think it was 336. Yep. Oops. What?